Thank you. Well, you know, those of you who were here yesterday and heard my talk know what I've spent most of my time for the last couple of years doing, so I don't have so many new things to report. I will talk about, my major goal is to talk about mechanical graphene. So this is actually a system, a mechanical system that reproduces the spectrum of the electronic spectrum of strained graphene. And it's actually, it was published in, I guess 2017. So it's not totally new, but probably most of you haven't seen it. And the advantage of this thing is that the arithmetic for doing all of the things that go with the topological properties is really much simpler. It's scalar instead of vector. So what I'm going to do is to review a little bit of the Maxwell lattice stuff that you've heard referred to, and then go to the mechanical graphene. And if there's time at the end, I will talk about a model of jamming on a lattice that analytically predicts the jump in the bulk modulus when you hit the jamming point and the continuous growth of the shear modulus, which we can do with effective medium theory, and it's the first model that I know of where you can do that. Okay, so let's see. I push this button, and do I go forward? Yeah, I see. I can always push this one. That doesn't matter. Okay, so we're going to start with review the Maxwell lattices. These are mechanical lattices that consist of nodes and springs, and the number of neighbors is equal to twice the dimensionality when you have periodic boundary conditions. And typical examples are the, let's see, no, I have to hit the pointer. Oh, there we go. The Kagame lattice, its twisted version, the square lattice, its distorted version, pyrochlore in the other. And depending upon the geometry, you have different modes and different topological properties and different structures of the excitation spectra. So I want to just establish a language that I'm going to use for the graphene. So we have a strain variable or a stretch variable. I'm not quite sure why I've called it E, but this is so I have a bond which has a unit vector along B. I have, and the bond is centered at position RB, and so the stretch of the spring connecting RB to its, a position here to that position is RB plus a half B, U of RB minus a half B, and we'll call that the stretch. So it's a scalar, but it involves the vector U, and the energy, of course, is just the square of that stretch with an elastic constant in front. And we can define a tension on the bond by taking the derivative of the energy with respect to the stretch, and that comes out to be KERB. And there's a vector tension that points in either the plus or the minus B direction with magnitude T, and once we've established a sign convention, we can continue on. And then there is a force, which is dE du, and you can spend a little time thinking about whether there's a minus sign there in front. There is, in fact, normally a minus sign, but this is considered by the engineers the load, and so the sign changes, and it's more convenient to define it this way. And that's equal to the sum over all of the bonds that are incident on the site times the vector tension. And you can see that these equations define a linear relation between the stretch and the displacements U, and between the force and the tensions T. And for the Maxwell lattices, the ones where Z is equal to 2D, we exactly match the number of degrees of freedom with the number of constraints. So these matrices are square matrices, right? And it turns out that C, this compatibility matrix, is the transpose of the equilibrium matrix Q. Now, once we've got that, we can appeal to linear algebra. We have a dn-dimensional displacement vector at each site, a dn-dimensional force vector at each site, an NB, N is the number of bonds, stretch vector at each bond, and a tension NB dimensional 1 at each site. So we now have an N dn by NB, which is a square matrix, times U is equal to E, QT equals F. And then you can appeal to linear algebra and note that the rank of a transpose matrix is equal to the rank of the matrix. And the null space of C is the set of U's that don't stretch the bonds. So that null space defines the set of zero energy states in the system. And the null space of Q is the set of tensions that give you no force, and that's what the engineers call a state of self-stress. This is a state of the system that's capable of having stresses in the bonds, leaving the sites with no force. The simplest example of that is to take a ball and string, wrapping it around a cylinder, and stretch the radius of the cylinder. There's zero force on each site, but all of the springs are stretched. So from that, we can derive this important index theorem that says that the number of zero modes minus the number of states of self-stress, so this is really the dimension of the null space of Q, is equal to the number of degrees of freedom minus the number of constraints. And for us, that's 0 as long as we stay with periodic boundary conditions. You can then, because we're talking about a periodic lattice, you can take a Fourier transform, and the big matrix breaks up into smaller matrices indexed by the wave vector Q. So now we have C of Q, U of Q is E, and we can apply the same argument telling us that the number of zero modes at wave vector Q minus the number of states of self-stress at wave vector Q is equal to the number of degrees of freedom in the unit cell minus the number of constraints in the unit cell, and that's equal to 0. So that tells us immediately that in these systems, the number of zero modes is equal to the number of states of self-stress, and that's a powerful tool for calculating the properties of the system. So, the systems that we looked at included the twisted Kagame lattice, this intermediate lattice, and what we call a topological lattice over here. This one has a polarization vector RT, and this one has a zero polarization vector as we defined it. And you can calculate the number of zeros by taking the path integral of the log of the determinant of this 6 by 6 matrix to determine how many zeros we have. And there are, once you've got the topological RT from this, you can look and see whether or not you have a polarization component that comes from the nature of the termination of the cells. And I won't spend any time on this now because we'll see it again when I go to the graphene in a context that's a lot simpler. So this is just a review of what we've done before. And yeah, this again shows that there are these mysteries that the Hamiltonian we look at, the energy is C dagger C, but you can sort of take its square root. This thing right here looks very much like what you see in the quantum mechanical systems all the time, and then we square it to get this, and the Hamiltonian we're interested in is the 1-1 component of that. And this is a bunch of language having to do with how to get the topological part, which will be cleaner when we look at the graphene model. I just want to point out that the simplest model we looked at were these ones which have 3 sites per unit cell. If you go to more complicated systems with 4 sites or more sites per unit cell, rather than having only zero modes at the edge in the topological state, you have these zero energy states at the center of the zone, in the center of the Brillouin zone, which are local points where the energy goes to 0. And you get a phase diagram like this, which is a little hard. So let's look at this system right here. We have the 4 points of the square. That was the distorted square I showed you earlier. We fix 3 of the points and move the other point around. So that gives us a 2-dimensional phase space. And that 2-dimensional phase space is complicated. It was really pretty hard to calculate all of the properties here. The gray areas show areas where you have what are called the Weyl modes. These are regions where you have 2 zeros in the middle of the Brillouin zone at a point, and they move around as you move about. Then you hit a boundary, and you end up with polarizations. These are the topological polarizations, which I mentioned for the Kagame lattices, which determine the nature of the edge modes. So you go from having regions where there are zero modes on the edge, which are topologically determined, to regions where you have zero modes in the bulk, which also have a topological property, because when you integrate the determinant around the 0 point, you get a topological invariant. But this is pretty complicated, and it took us a long time to do this calculation. And in the graphene example now, we can do the calculation here in this room. So, graphene, this is a gift to the quantum people. The origin of the topological insulators came from graphene. It's actually, the history of this is interesting. Notice here, this one was the first written. This was the one that really convinced people it was interesting. This guy was rejected. When this one was accepted, they went back and allowed this one to be published. So it shows how things go. So this is graphene. It's a honeycomb lattice, and you have a unit cell that has 2 sites per unit cell, and you have 3 bonds per unit cell. So, and what the electronic stuff basically boils things down to where you have 1 degree of freedom per site. So what we want to do is to create a mechanical version of this thing. So here's what it is. We take the honeycomb lattice, and we have 2 sites in the unit cell, the blue site and the red site. So we're going to center an equilateral triangle at the blue site, and then the red sites come and they connect the vertices of the triangle to others. So imagine that these are pieces of metal that can bend. Or I'll tell you another version in a minute, but just for the moment, think of it as being able to bend. So what happens is I'm sorry. Okay, let me talk about the bend one first. So let's imagine that we pin the triangles at the blue site. And then the degree of freedom that we allow is for the red site to move up or down. So that says that we have there's 1 red site and 1 blue site per unit cell. The blue site concentrates, giving you a constraint. It forces that site to be unmoved. And the red site can move up and down. So we now have a situation where we have 1 constraint and 1 degree of freedom per unit cell, which then has the same count that you had before. So what we have to do is to assign an energy to the distortions of that triangle. So it's the bending energy that comes out. Now it turns out that we thought at first when we had the idea of bending it that we could get an analytic calculation of what the energy of the bending of a triangle is. And you can, in fact, but it's a horrible mess because you have to worry about the boundary conditions and all of that. Then we came up with a simpler version. So here, what we do is we put a pivot point somewhere other than the center. Actually, I'm sorry, we did that even for the bending. So this yellow point is a pivot point, which we're going to put at a position RP is x1, d1, x2, d2 plus x3, d3, where the d's are the vectors from the center of the triangle to the vertices. And, of course, we're going to restrict the sum of x1, x2, and x3 to be 1. Okay? Now, let's imagine that we put a spring there. This is an indication where we have a spring. Here's the triangle that the spring is attached to. And if we move the system so that the spring stretches, that'll cost you energy. And that will happen. Let's go to the next step now. So we want to come up with an energy, and the energy has to depend only on the height variable at each site. So RA is the site on the red lattices, and RB are the sites on the blue lattice. And just to keep yourself in order, it might be useful to remember these. The D1 points up, the D2 points over to here, that's that, and the D3 points over there. So if we rigid rotations about the pivot point leave this thing unchanged. So you can do rigid rotations. So that tells you if this guy is equal to 0, if this EB is equal to 0, then there's no energy cost. The thing hasn't been stretched upward. So what we're going to do is to say this EB now, which involves 3 sites instead of 2 sites, is the stretch energy, the stretch. It's exactly analogous to what we had for the stretching like this, except there are 3 sites. And we're going to create an energy which is the square of this guy. And as I said, we actually did the calculation of the bending, at least approximately, to show that that works. And then also you can easily look at what happens when you pull the spring. So it really is true that the energy is the square of this guy. Okay? So let's write that down. We have an energy E of RB equals the sum over the sites of xi, that's what we had back here, xi times z, where these are the neighbors, these are the RB plus a D is a red site neighbor to the blue site. So that's the stretch. The energy has to be the sum over all of the blue sites of the square of this. And we can calculate a tension that goes with that by taking the derivative with respect to E, just as we did in the spring case. And the forces can look like this. So now you can see that these two things define, rather these two sets of equations define for us a relationship, a linear relationship between E and U, E and Z rather, E and Z. And this defines a linear relationship between the tensions, which are defined by this, and the forces. So now we have the same thing we had before, that we have a matrix that takes E to U, or E to Z, and a matrix that takes T to F, and they are transposes of each other. So we have exactly the same theorem that we had for the stretching, namely that the number of zero modes minus the number of states of self-stress, defined in the same way as before, is equal to 0 for this system, because we have a balance between the number of degrees of freedom and the number of states of self-stress when we're under periodic boundary conditions. But notice now, rather than having a vector that relates the stretch to the degrees of freedom, we have a scalar degree of freedom. So this is what we do here. We define E is equal to C times Z, F is equal to Q times T. The C is this matrix, easy to write down, and C of Q is just the Fourier transform this. It's sum over the x's times e to the xi e to the I q dot di. So we have a single scalar function of the q's, and we can define a quantum-like Hamiltonian as a C star C, and the mechanical Hamiltonian is the 1-1 component of this. So if we're interested in zero modes, then all we need to know is the properties of C. If we want to get the full spectrum, we need to use this H. So the Weyl modes, if they exist, will be solutions to this equation where the Q have real values, so that there is no decay. So we're on the basically. I should say we should think of this as putting things on a torus, where we have Q running around the torus, and e to the IQ dot, so we can define those z's, and all of the z's are real, lying on the torus. And then if we have a singularity that makes those things complex, then we have sort of a vortex that's running through the center of the cylinder, or of this torus, or penetrating the center of the donut. So what kind of zero modes can you get? So for example, if we set the position of the pivot point to be exactly at the center of the triangle, there have to be zero modes there, and here's one of them. You can see how it works. If I rotate this, let's think this one. If I rotate this one counterclockwise with respect to this axis, I raise that site and lower that site. Well, over here, what I need to do is to rotate about this axis. If I do that, and I do it so it's counterclockwise, then this guy goes down and the other guy goes up. And you can convince yourself, looking at all of those, that that is indeed a zero mode of the system, because we are rotating them all so they remain planar. Here is if we set the pivot point on the boundary here, then it's very much like the untwisted Kagame lattice, which you may remember that we had zero modes running around. But because of the fact that the Kagame lattice has these straight lines which are able to support stress without moving the bonds, in other words, states of self-stress, then we have square root of n zero modes. And the same happens here. If we go to this particular point, you can see that if I rotate about this axis, this guy goes down, this guy goes up, so the neighboring one has to be the opposite. I rotate about this axis, that goes down and up, so there I have a zero mode that's there. Now, I don't have pictures of the states of self-stress. I really should have done that, but believe me, there are states of self-stress that go with it. So you can see that we have pictorial representations of the zero modes that are pretty straightforward. So that means that we can have a phase diagram. So I'll tell you what the phase diagram is, and then I will try to justify where it came from. So this is the x1, x2, x3. And I'm going to concentrate on the region that lies within so that all of the x's are less than 1 or less than or equal to 1. We can extend the phase diagram outwards where one of the x's is greater than 1, then the others have to be negative. But for here, so at the origin here, at x at the 1/3, 1/3, 1/3, that actually maybe it's even worth going forward here. So at the 1/3, 1/3, 1/3, this C of Q is this. Now remember, these D's point to the terminations of the equilateral triangle, so that means that this sum is automatically 0. So it says we have a zero mode at, well, you can actually calculate which Q's will give you a zero mode here, and it turns out to be Q's at the K points. So if we go back here, this is the Brillouin zone, the hexagonal Brillouin zone that goes with it, and what that we've just shown is that at the point 1/3, 1/3, 1/3, each of these K points has a zero mode, and of course, remember that points that are separated by a reciprocal lattice vector are equivalent. So here the K and the K, for example, this vector from here to here is a reciprocal lattice vector going across the Brillouin zone. So these 2 points are equivalent, and these 2 points are equivalent, et cetera. So there are really only 2 points, even though it looks like there are 6. Okay. Now, so that now this guy, if I do an integral around that point, I have a topological invariant. It's the winding number. And so that says that there has to be a zero mode nearby the point 1/3, 1/3, 1/3. If I move away from it, I don't have anything. So at the other end, if I look at x equals 1, 0, 0, then only one of these other guys disappear because remember the x's go in front. So I have an e to the iq dot d1, and that cannot have any zeros. So that tells us that if we go up to this point, there are no zeros. In the vicinity of this point, you have to have zeros, which tells us then that there has to be some boundary that separates the two. Okay? And you can see how that goes. You want to know, so I have, in the vicinity of this point, I have 2 zero modes, the one at k and the one at minus k. And now, as I start moving around in here, these guys are going to move, and they're always going to be a q and a minus q. Now, at some point, if I'm going to have a separation between the regions where I have no zero modes in the bulk spectrum and zero modes in the bulk spectrum, I have to get rid of the Weyl modes, the points. So the only way I can do that is to bring them together so they merge. So you can see how that could happen. If I move this guy over to here and this guy over to here, then this point and this point are the same, and I've moved them so they hit the same point and they annihilate. So the boundary between this point and that point should be the point at which these two guys merge to the m points. And that indeed is what the arithmetic shows here. I'm going to look for a point such that q star is equal to minus q star. That's the Weyl point, plus a g. If they are that, then these two are equivalent, or they're at the same point. And you can see that gives me that q star is equal to a half g. And here, you can go back and see that going from here to here is a full g, the reciprocal lattice vector. So this is that going from there to there is half that. So you get the right picture that goes with the calculations. So then you can say, well, let's look at what, let's call this QMJ. It points in the direction of the DJ. So this is a DJ hat and has this magnitude because it's half the reciprocal lattice vector. And you can calculate QMJ.dk. You get this answer. And that gives you that xk minus xk plus 1 minus xk minus 1 is equal to 0 at that point. Then we still have that the sum of the three x's is 1. And that tells you that xk is equal to xk plus 1 plus xk minus 1 is equal to a half. And we can go back here and see that this line right here is x equals a half, and then you can convince yourself that indeed the xk plus 1 and xk minus 1 give you the distance from this line to the point, etc. And those two are also a half. So this gives you the dividing line between those two things. And then you have the symmetry that goes with it. So now what happens when we're in this region? We have the Weyl modes. Over here now we don't have any Weyl modes, but what we will find is that we have zeros that correspond to a complex number to e to the iq dot d being less than 1 its magnitude, which means that it's either decaying or growing. So a word about that. So you can calculate the topological properties of this C, or the ones we're interested in, by calculating the winding number along some path. So when you have the Weyl points, you have a winding number around a particular point in the Brillouin zone. You can think of that as being on the surface of the torus, that is the reciprocal lattice, right? But if you can also take a path that goes from one end of the Brillouin zone to the other. You've then created a circuit that goes around the torus instead of a circuit that is on the surface of the torus. And so in order to understand how we're going to get the surface states, we need to look at the fact that the C that we introduced really is not, it's a gauge variant quantity, because I'm perfectly free. Gee, this thing dangles down, and I think my shoelaces have come untied. Let's see, when I go back here. Let's see, what was I going to say now? I now lost my train of thought. Oh, yeah. So the C involves, its value depends upon where I put this point and where I put this point. Now, there's no reason in terms of the arithmetic that I have to put this point exactly there. I can say, well, I'm going to have a lattice that is centered here, and I can put this point anywhere. If I change the position of those points, I change the value of this. And you can see that the C prime of Q, I can define a delta RB and a delta RA, and I can express the new C in terms of the old one, and we'll call that the difference in phase between the two be minus IQ dot RL, and RL is RA minus delta RA minus delta RB. Okay. Now, why do I want to do that? Let's look at the original C of Q, e to the iq dot d1, and for convenience right now, I will go along this line, along the line that x2 and x3 are both a half, just to make the argument simpler. So now I want to know what the zeros of this are. Now, notice there's an e to the iq1d here and an e to the minus iqd there. If either of these become, they become less than 1 in magnitude, then here I have something that is going to 0, say, as I go to that critical Q, and this one's going to infinity because it's 1 over that. And you don't want to do that. So if I do a gauge transformation and multiply the C of Q by e to the iq dot d1 over 2. So I multiply times that number. Now I've separated things out so I have only a positive e to the I here and not a negative 1. And I can solve for this. It's minus x1 over 1 minus x2 cosine of qx over 2. And you can see that this becomes greater than 1 in magnitude when x1 gets to be greater than a half, which means that the Q is complex. I have a thing that's decaying away in the d1 direction, and that's what gives me a 0 mode. It gives me a surface 0 mode. And its properties are determined by this integral, which gives me the RT. RT is N1A1 plus N2D2, where I take the two circuits around the torus. And the RL is determined by what I have to do to get rid of the nasty terms over here to put only the positive powers of e to the IQ here. So all of that stuff occurred in the Kagame lattices and in the stuff that Charlie and I did earlier. But it's only one scalar variable and not a 6 by 6 matrix I'm dealing with, so it makes it a lot simpler to deal with. So now you can go and do all of the counts. You probably will have forgotten already, but let me just say that we can, RT is equal to minus dj, so there are three different values of the RT corresponding to the three different directions here. Then I can look at what the surface charge is for each of the directions, and that gives me, and RL is minus d1 over 2, d1, d2, or d3, depending upon which of the surfaces I'm looking at. And then I can take this formula, which followed from what we had earlier, calculate it, and we can get the number of zero modes for each value of the RT. And you can see it on the bottom surface, I have 1 if I have RT equal to D1, and 0 if it's D2 or D3, et cetera. So you can just go through the arithmetic and find the number of zero modes on a given side. And this really encapsulates most of what's going on in the topological world. To do the topological insulators, then you want to worry about introducing a gap elsewhere, and you have somewhat, instead of mapping onto the complex plane, you map onto a sphere, and things are a little more complicated. But the ideas are the same. So how am I doing for time?
7 minutes.
Oh, I have 7 minutes. Okay, good. I will then, I think, I hope you've gotten the message about this. I'm now going to switch to the jamming. So I'm sure you've all seen talks about jamming. You take a bunch of points, you allow them to expand, and at some point they touch each other and they can't grow any further. You can't increase the size anymore. You can't decrease the volume anymore without running into the interactions amongst the spheres. And at that point, the system resists isotropic compression, which means that the bulk modulus jumps discontinuously when you hit the jamming point. When you push further, you need some theory, some model about how the spheres interact, and usually what people do is just say, well, I'll put a spring between them, and when I start pushing further, the springs will begin to compress, and then the shear modulus rises continuously. So, there's this famous jamming phase diagram, and the T stress and concentration plane. There is this point at t equals 0, which is the jamming point, and it has many properties. The number of neighbors grows as phi minus phi c to the 1/2, where phi is the volume fraction. The shear modulus grows continuously away from that point. The bulk modulus jumps to a constant, and there are characteristic frequencies and so forth out of that. Now, at the other end of the spectrum, there is another model system that has a rigidity transition. So suppose I take a hexagonal lattice with springs, and I go in and I cut the springs. Now, if those were resistors, at a certain point, the conductance of the lattice would vanish, and that's what's called the percolation threshold. It has to do with scalar variables. But if you make them springs, then you have sort of a vector percolation problem. You keep on cutting, and at some point, the rigidity of the lattice goes to 0. And the interesting thing about that is that both the shear and the bulk modulus trail each other, and both of them go to 0 at that critical rigidity percolation transition. And so that's what much of the analytical work is done, but it misses the discontinuous jump that occurs with the thing. So what is the reason for that? In the jamming protocol, the way you create the lattice guarantees you that the minute those spheres touch enough that they resist compression, you have to have a bulk modulus that's non-zero. So by construction of the lattice, that happens. And then as you squeeze a little bit further, it becomes harder to do that. So in order to make a lattice model that you can do things like effective medium theory on, what you want to do is to guarantee that you have a pathway to a lattice point where you have a lattice that you know will support compression, even though it's undercoordinated. So what we'll do is to take the honeycomb lattice again. The honeycomb lattice without the next nearest neighbors it has a non-vanishing bulk modulus, but the two shear moduli are 0. Then I can add next nearest neighbor forces, and notice that when you do that, you get two triangular lattices, which are sort of orthogonal to each other. And when we add these, then I can take the lattice with both present, and I can give a probability PA to be in the honeycomb lattice, PB to be in the blue triangular lattice, and PC to be in the red triangular lattice. And I'm allowed to look at the phase diagram in the whole lattice, and that's what we have here. This is the phase diagram that comes out, which I'll explain in a little more detail in a minute, but this is the PA, PB, PC plane. This is the standard jamming point that we're interested in, and all points above here are rigid, and you have phase transitions that involve only the hexagonal lattices, one or the other, and all of them together. So here's a cuts of the phase diagram. Here, this is, if I take a cut at the top, so I set PA equal to 1, then, let's see, I'm sorry, if I set PA equal to 1, I'm up here, and what am I saying right? That, yeah, so the, right, so the rigidity transition now, as described here, if I set PA equal to 1, I always have the bulk modulus as non-zero, right? So, but there still is a rigidity transition which occurs when the shear modulus becomes non-zero. So at PA equals 1, this is the line which separates B non-zero and G 0 from B non-zero and G non-zero growing. Okay, so all of this region up there. So, but more interesting is to take other cuts of the phase diagram. So let me take this one. I'm going to set B equal to PC. So that means I'm putting the probability of taking a bond from either of the two triangular lattices to be the same. And then we have this two-dimensional phase diagram that looks like this. This is PA. Along this line, PA equals 1, I have a non-vanishing bulk modulus. I hit J, and I go into this phase RT where everything is rigid, and the shear modulus grows continuously away from here. Then there's this line that goes from here down to PA equals 0, but there's a critical value of PB for which I have the rigidity percolation transition. And this whole line is a rigidity percolation transition. In other words, along this entire line, if I cross it, both the shear modulus and the bulk modulus grow linearly with the distance from that line. And then I hit this point, I get the discontinuous jump. So if I tell you that I'm going to model jamming, I'll just tell you I'll take a path that starts in the floppy phase where there's no rigidity at all. It goes up to there, and it hits that point, and all of a sudden I have a bulk modulus that's non-zero, and then I can travel around in here to make the path like that so that I've actually created a way. Now, it's possible to take this, to modify the model, to take this and move it over to there so it looks exactly like what we had. So here is what the, what the analytics give you. If I call delta PAJ to be 1 minus P, so that's the 1 minus PA, so that's the distance from this upper thing. Delta PJB to be the distance from along PB from that point, and delta P tilde is the distance from the rigidity percolation point. So you do the calculation, you find that KJB is delta P tilde over some number. So that tells us that I have a triangular lattice, and when delta P tilde becomes greater than 0, I get a non-vanishing KJB, and then I also get a rigidity modulus and a bulk modulus that I can calculate. The bulk modulus comes from the KJA. In other words, the A lattice is the honeycomb lattice, And if this has a non-vanishing average value, then I have a bulk modulus, and it looks like this. So you can see what happens here. This, if I write it all out, it's delta p tilde, which says that if I pass across here, it will grow linearly. But if I go in and I hit it at delta p a j equal to 0, so that says that I'm going along this line or I'm hitting up there, then this goes away and this ratio becomes 1. So this arithmetic gives us how you cross over in the vicinity of that point from having, you know, all along the line coming in, I have a continuous change in both the bulk and the shear modulus, but if I go up to the other line, we have the discontinuous change. And to finish it off, you can ask questions about what happens if I apply some dynamics to the system and put it in a viscous fluid. So this is one of many models that people use to try to talk about what happens to the viscosity in a system. So you put it in a viscous fluid and you ask, how does the presence of the network change the viscosity? And it's interesting that if I look at you get different behavior for the shear and the bulk viscosity. For the shear viscosity, it diverges as 1 over delta p tilde with an omega. You know, gamma omega here, if I look at the coefficient of omega, I get the viscosity, the shear viscosity, which diverges as delta p. If I do the same thing for the bulk modulus, we get this kind of expression for small omega, which tells me that I actually get a viscosity that diverges twice as fast, if you wish. So I think that I'm probably just about out of time, and I will stop.
Time for a couple of quick questions. Yeah. Go on.
So one thing that people talk in the jamming community now about is dynamic jamming. Is there sort of a way to probe?
So remind me what that means.
So this is, you know, when you can walk on water and cornstarch solution, right? Because the strain rate is so fast that it jams due to the applied strain rate. Is there any way to sort of probe the kind of thing?
Okay, the answer is I have not thought about that. Maybe, who knows? Yeah. You know, these little models are often quite useful to set your thoughts in order. I find this explains essentially, for me, everything that goes on in the jamming, or most of it. Yeah.
Yeah.
Question. Is there a scalar version of a 3D topological mechanical lattice?
Good question. I haven't yet found one, but I haven't looked that hard. I think if you use the diamond lattice, probably. But I don't know exactly, you know, so I'd have to take the diamond lattice and extract the tetrahedra and have some tetrahedral thing, is what I guess, but I haven't done it.
Okay, so in the interest of time, I think we should move on. Thank you again.